Now you'll remember that a phasor is a geometric representation of a complex number. And therefore phasors, when they're represented as complex numbers, can be easily added algebraically, and we've seen how to do that. But there's also a geometric method, and to add phasors geometrically, we place the tail of the second phasor at the tip of the first phasor, and then the sum phasor is drawn from the tail of the first phasor to the tip of the second phasor. So probably a diagram will make this a little clearer. Okay, here's an example. I would like to add 5 plus j3 and 2 plus j6. 5 plus j3, let's see, 1, 2, 3, 4, 5, 1, 2, 3. So there's the phasor representing 5 plus j3. And 2 plus j6, 1, 2, and then 1, 2, 3, 4, 5, 6. There's 2 plus j6. So now the rule says place the tail of the second phasor at the tip of the first phasor. So basically what we're doing is we're transferring this phasor up to here. And then the sum phasor is from the tail of the first phasor to the tip of the second phasor after having been translated. So this dotted line here is the translated phasor, and then this long diagonal line, that is the sum phasor. And the answer that we get, of course, is 7 plus j9, which is easily arrived at algebraically. Okay, and there's the description in the notes. Okay, now the next idea is polar form of phasors. We've already seen that a phasor can be represented by a complex number with real and imaginary parts, and we know that a phasor can be represented geometrically as an arrow in the plane. But there is a third way, and that is using polar form. So suppose that P is some phasor drawn in the plane, and we could specify P by its real and imaginary parts. Okay, so let's just draw up an example here. Okay, so there's a phasor P, and real and imaginary parts. Well, this point is x, y, and so the real part is x and the imaginary part is y. But there is another way to give this phasor, and that is using its length and the angle that it makes with the x-axis. Okay, so we're going to let this symbol here, which you read as the magnitude of P, okay, and that's going to be the length of the phasor. And then we can specify P in polar form using its length and its angle. That will give a unique representation of the phasor. Now, since the tangent of theta is given by y divided by x, that means that we can write, let me write that down, since tangent theta is equal to y over x, then we can say that theta is equal to the inverse tangent of y over x. Okay, so let's do an example. We have P given by 3 plus J4, and we want to find magnitude of P and theta. And so there's P, and this point here is point 3,4. So that means if I drop a vertical line there, then this segment here has length 4, this segment here is length 3. So that means that we have a right triangle here with legs 4 and 3, and therefore the magnitude of P is the square root of 3 squared plus 4 squared, and we know that is 5, right? So that means magnitude of P is 5, and then it's just a matter of finding theta. Theta is the inverse tangent of 4/3. And we know how to find that on our calculators. And so inverse tangent 4/3. And the answer is about 53.1 degrees. Okay, and just one other thing. Rather than writing magnitude of P equals 5 and theta equals 53.1 degrees, the polar form is often written in a more compact form like this. You give the magnitude and the little angle symbol, and inside the angle symbol you write the angle.